Look at your hand. Go on. Hold it there in the light. Turn it over. See the lines on the palm, the shape of the knuckles, the subtle texture of the skin. It seems so solid, so present, so unquestionably real. You have lived with this hand your entire life. You know its weight, its strength, its warmth. It is a tool, a comfort, a part of you. And it is a lie, not a malicious lie, a necessary one, a beautiful, intricate, and deeply convincing illusion sculpted by your senses so that you can navigate the world. But an illusion nonetheless. Because beneath the skin, beneath the cells, beneath the intricate dance of molecules, you're made of ghosts. You're built from whispers, from probabilities, from things that flicker in and out of existence, things that can never be held, never be isolated, never truly be seen. There are prisoners trapped inside the very heart of your atoms, bound by a force so powerful it literally creates reality out of its own tension. These fundamental components of your being cannot exist alone. If you try to pull one free, the universe will simply make more of them, weaving new matter from the energy of your effort. They have a name, a strange, whimsical name for such a foundational, terrifying concept. They're called quarks, and their story is not just the story of a particle. It is the story of what it means for anything to be real at all. It is a journey that forces us to ask a deeply unsettling question. If you are made of things that cannot exist on their own, are you truly there when no one is looking? What is the substance of a shadow? What is the architecture of a dream? What truly are you made of? To begin this journey, we must first unlearn the world. We must peel back the curtain of our own perception and confront the comfortable fiction of solidity. You believe in things. You believe in a rock, a table, a planet. You believe that if you take an object and break it in half, and then break that half in half again, and continue this process with an infinitely sharp knife, you will eventually arrive at some final, indivisible speck. A fundamental building block. A tiny, hard, simple thing. This was the dream of the ancient Greeks. They called it atomos, the uncuttable, the final answer, the bedrock of reality upon which everything else was built. For centuries, this idea was a philosophical comfort. It gave the universe a sense of order, of foundation. It told us that reality, at its core, was simple and solid. Even when we discovered the atom, the name stuck, and for a while, the illusion held. We pictured them as tiny solar systems, a dense, hard nucleus like a sun, with electrons orbiting like planets. A thing, a miniature object. Then we looked closer. We built machines, great cathedrals of science, circular tunnels miles long designed to hurl particles at nearly the speed of light and smash them into one another. We did this for a simple reason, to see what they were made of, to perform that act of breaking something in half again and again. We smashed the atom and found it was not a solid thing. It was almost entirely empty space. The feeling of solidity you experience when your hand rests on a wooden table is not a meeting of substance. It is a war of invisible forces. The electron fields of the atoms in your hand repelling the electron fields of the atoms in the table. You have never truly touched anything in your life. You have only felt the push. This was the first crack in the illusion. The universe was not solid. It was a vast and echoing void, sparsely populated by frantic, energetic motes. So we focused on those motes. We looked at the nucleus, the part we thought was the hard center, the proton and the neutron. Surely, here we would find our foundation. Here was the tiny, indivisible speck. But when we smashed them, they too fell apart. And what we found inside was not a set of smaller, simpler pieces. It was not a neat collection of tiny gears. What we found inside was chaos. A proton is not a quiet house with 3 occupants. It is a raging, violent, subatomic hurricane, a seething, bubbling cauldron of particles appearing and disappearing in less time than it takes for light to cross an atom. For every quark that is supposed to be there are countless others, virtual particles, born from the raw energy of the void and vanishing just as quickly. There are seas of antiquarks, There are rivers of the particles that hold them together, the gluons. The thing you call a proton is not a thing at all. It is an event, a stable, ongoing storm. The illusion of a single, solid particle is just our name for a pattern of ceaseless, violent activity. This is the first layer of the truth. The world is not made of objects. It is made of relationships, of dances, of energetic patterns. The lie is that reality is a noun. The truth is that reality is a verb. But how did we arrive at this bewildering picture? How do we trade the comfort of solidity for the madness of the quantum storm? Like all great shifts in understanding, it did not happen overnight. It was a slow, reluctant, and often painful birth. The year is 1964, but the story begins earlier in the decades after the Second World War. Physics was in a state of glorious confusion. The new particle accelerators, born from the technologies of war, were acting like cosmic fishing nets, and they were pulling in a bizarre and ever-growing catch. For every familiar particle like the proton, neutron, and electron, dozens of new, exotic particles were being discovered. They had strange names like kaons, pions, lambdas, sigmas, and xis. They had strange properties and lifetimes measured in fractions of a billionth of a second. It was chaos. It was known, with a touch of exasperation, as the particle zoo. Each new discovery was another animal in a cage, with no clear relationship to the others. It was a collection without a catalog, a library with no system. Physics, the science of finding fundamental laws, seemed to have stumbled into the business of stamp collecting. What was the organizing principle? Was there one? Or was the universe simply, at its heart, messy and complicated? Into this chaos stepped a man named Murray Gell-Mann, a brilliant polymathic and famously confident physicist at Caltech. Gell-Mann was a pattern seeker. He saw music where others heard only noise. He looked at the chaotic properties of the particle zoo, their mass, their charge, their spin, and began to group them. He used a branch of abstract mathematics called group theory to organize the particles into elegant, symmetrical patterns, like sorting crystals by their facet arrangements. He called his classification scheme the Eightfold Way, a nod to the teachings of Buddhism. It was a name that hinted at a deeper, more philosophical order hiding beneath the surface of the data. The Eightfold Way was a triumph. It took the messy zoo and turned it into a periodic table for subatomic particles. It even predicted the existence of a new particle, the omega minus, with a specific set of properties. In 1964, physicists at Brookhaven National Laboratory found it, exactly as Gell-Mann's theory said they would. It was a stunning confirmation. The pattern was real. But this success created an even deeper question. Why? Why did this pattern exist? The periodic table of elements works because all atoms are made of the same simple components: protons, neutrons, and electrons. Their different properties emerge from different combinations of these building blocks. Gell-Mann, along with another physicist named George Zweig, who was working independently at CERN, made a radical, almost reckless leap of logic. What if the particles in the Eightfold Way were not fundamental? What if they, too, were made of even smaller, even more fundamental components? This was the birth of the idea, the ultimate answer to the particle zoo, a simple, elegant theory that could explain everything, but came at a terrible price. The model required these new, hypothetical particles to have properties that had never been seen in nature. Specifically, it required them to have fractional electric charges. All known particles had a charge of -1, +1, or 0 in elementary units. These new particles had to have charges of +2/3, or 1/3 point. It was unheard of. It was, to many physicists, absurd. Gell-Mann himself was deeply ambivalent. He treated the idea almost like a mathematical trick, a convenient fiction that made the equations work. He needed a name for these strange, fractional things. He found it in a line from James Joyce's famously obscure novel, Finnegan's Wake. 3 quarks from Mustermark. Quark, a nonsense word from a stream of consciousness book. It was a perfect name for a particle that might not even be real, a ghost in the machine of mathematics. And so, the central paradox was born, a theory that explained the subatomic world with breathtaking elegance, but which was built upon components that seemed to be forbidden by nature itself. A theory that demanded the existence of quarks in a world that refused to show them. Where were they? Scientists began the hunt. They scoured data from every particle collision. They looked in cosmic rays showering down from space. They examined moon rocks and sediment from the deep ocean floor. They were searching for a flicker of evidence, a single particle with a fractional charge that would prove the theory was not just a clever trick. They found nothing. Not a single, solitary, free quark. It was a crisis. The most successful theory of particle physics was based on things that did not seem to exist. It was a beautiful house with no foundation. A perfect answer that posed an impossible question. The quark was a necessary ghost, and for years, it haunted the world of physics. It explained everything, yet it was nowhere to be found. How can something be both essential and absent? The answer, when it finally began to emerge, would not be found by capturing a quark. It would be found by understanding why it could never be captured. The answer was not a particle, but a force. A new kind of force, unlike anything ever conceived. The universe, it turned out, had its own prisons, and its most fundamental prisoners were the quarks themselves. To understand this prison, you have to understand its rules. The world of quarks is governed by a strange and beautiful taxonomy, a set of classifications that sound more like something from a fairy tale than a physics textbook. First, there are the flavors. These are not tastes, of course. They are different types or species of quark. There are 6 of them in total, organized into 3 pairs. There is the up quark and the down quark. These are the most common, the most stable. They are the ingredients of everyday matter. A proton, for example, is made of 2 up quarks and 1 down quark. A neutron is 1 up quark and 2 down quarks. They are the bread and butter of the cosmos. Then there are the stranger, more exotic flavors. The second generation, the charm quark and the strange quark. And the third, even heavier generation, the top quark and the bottom quark. These heavier quarks are unstable. They existed in abundance in the fiery heat of the Big Bang. But today, they can only be created for fleeting moments in high-energy particle collisions. They are echoes of a more violent, more energetic past. 6 flavors. A simple family tree. But this is only half the story. The true key to the mystery, the reason for their imprisonment, lies in another property. A property that physicists, with another dash of poetic whimsy, decided to call color. This has nothing to do with visual color. You will never see a red quark. It is a label for a new kind of charge. The familiar electric charge governs the electromagnetic force. This new color charge is the source of the force that holds quarks together, the strong nuclear force. There are 3 primary colors of this charge: red, green, and blue. And for each color, there is an anti-color: anti-red, anti-green, and anti-blue. And here is the fundamental rule of the universe, the unbreakable law from which everything else flows. No particle with a net color charge can ever be observed in isolation. Nature forbids it. Every particle that exists freely in the universe must be color neutral, or, to use the metaphor, white. How do you make white? You can combine a red, a green, and a blue quark. This is what a proton or a neutron is. A particle made of 3 quarks, one of each color, is called a baryon. It is color neutral. It is allowed to exist. Or, you can combine a quark of 1 color with an antiquark of its corresponding anticolor. A red quark with an anti-red antiquark, for instance. This combination is also color neutral. A particle made of a quark and an antiquark is called a meson. It too is allowed to exist. That is the entire list of possibilities. Any other combination is forbidden. A lone red quark? Forbidden. A pair of a red and a green quark? Forbidden. This is the rule. But why is the rule so absolute? The answer lies in the nature of the force that governs this world. The strong nuclear force. It is carried by particles called gluons. And the name is perfect because they are the cosmic glue holding the building blocks of matter together. But this is not your ordinary glue. Think about gravity or electromagnetism. As you pull two objects apart, the force between them gets weaker. The Earth's pull on a spaceship diminishes as it travels out into the solar system. The pull of a magnet gets weaker as you move it away from a piece of iron. This is intuitive. This is how forces are supposed to work. The strong force does the exact opposite. The force between two quarks behaves like an infinitely strong, unbreakable elastic band. When two quarks are very close together inside a proton, they barely feel each other. They rattle around in a state known as asymptotic freedom. They are free, but only within the walls of their prison. But if you try to pull one of them away, the force begins to grow. The further you pull, the stronger the force becomes. It does not weaken with distance. It strengthens. It is a jealous, possessive force that refuses to let its charges go. Imagine stretching that cosmic elastic band. You pour more and more energy into it. The tension builds and builds, stretching across the void between the quarks. You pull and pull, thinking you can snap it. But it never snaps. Instead, something even stranger happens. The energy you have poured into the field between the quarks, the gluon field, becomes so immense that it reaches a critical point. And at that point, Einstein's most famous equation takes over. Energy becomes mass. E uguale a mc al quadrato. The stretched field of energy spontaneously converts into a new pair of particles, a brand new quark and its corresponding antiquark. The new antiquark immediately binds with the quark you were trying to pull away, forming a new, color-neutral meson. The new quark remains behind, binding with what was left of the original particle. Think about what just happened. You did not succeed in isolating a quark. You only succeeded in creating more of them. You try to pull one prisoner out of the cell, and in the process, you created two new prisoners and a whole new cell. This is called quark confinement. It is not just difficult to see a free quark. It is, in principle, impossible. The very act of trying to observe one creates the conditions that prevent it. The universe is structured to hide its most fundamental components from view. So if we can never see one, how do we know any of this is real? How can we be so sure of a prisoner we can never interrogate? We see its shadow. We see the bars of its cell. In the late 1960s, at the Stanford Linear Accelerator Center, physicists conducted a series of landmark experiments. They fired high-energy electrons, like tiny subatomic bullets, into protons. If the proton were a soft, uniform blob of charge, the electrons should have passed through it easily, deflecting only slightly. But that is not what happened. Occasionally, an electron would bounce back at a sharp, dramatic angle, as if it had struck something small, hard, and solid deep inside the proton. It was the subatomic equivalent of firing a rifle into a bale of cotton and hearing the bullet ricochet. There was something hard inside, 3 somethings to be precise. These experiments, known as deep inelastic scattering, were the first direct, physical evidence for the existence of quarks. We could not see the quarks themselves, but we could see the effect they had on the electrons fired at them. We saw their fingerprints. We saw the wreckage they caused. It was like standing on the shore of a misty lake. You cannot see the boats on the water, but you can see the ripples they create as they move. From the shape and motion of the ripples, you can deduce the presence, the number, and the speed of the boats. The ricocheting electrons were the ripples. The quarks were the unseen boats, forever shrouded in the fog of confinement. The experimental evidence grew stronger and stronger. The model of quarks and their color charge, a theory called quantum chromodynamics, became one of the most precisely tested and successful theories in the history of science. It predicted the outcomes of particle collisions with astonishing accuracy. It worked. It explained the world. And yet, the central paradox remained, now amplified and confirmed. The most fundamental building blocks of the matter that makes up you and me and the stars cannot and will not ever exist as independent entities. This changes everything. This is not just a strange quirk of the subatomic world. It is a profound statement about the nature of reality itself. It shatters our most basic, classical intuition about what it means to be a part of something. Think of a house. It is made of bricks. You could take a brick from a house. The brick is still a brick. The house is now a house with a missing brick. The part is separable from the whole. Think of a car. It is made of engines, wheels, and gears. You can remove a gear from the transmission. The gear is still a gear. The car is now a broken car. The part is separable from the whole. This is how our minds are wired to understand the world, as a collection of components, an assembly of things. A proton is not like this. It is made of quarks, but you cannot take a quark from proton. If you try, you simply get another proton-like particle in a meson. The very concept of part breaks down. The quark is not a component in the classical sense. It is more like a note in a chord. A C major chord is made of the notes C, E, and G. But the sound, the identity of the chord, exists only in their simultaneous combination. The notes themselves are just frequencies, but the relationship between them creates something new. A quark is a note that can only be played as part of a chord. This leads to an even more unsettling realization. Where does the substance of the world come from? If you take the masses of the two up quarks and one down quark that are the main ingredients of a proton, and you add them together, you get a surprise. Their combined mass accounts for only about 1% of the total mass of the proton. 1%. So where is the other 99%? Where's the rest of you? It is in the energy of the storm. It is the furious, kinetic energy of the quarks rattling around inside their prison. And even more than that, it is the immense, seething potential energy stored in the gluon field, the cosmic rubber bands that bind them together. Most of your mass, the property that gives you weight and inertia, the very substance you think of as you, is not from the mass of your constituent particles. It is the binding energy holding them together. You are not made of matter in the way you imagine. You are made of relationships. You are a stable pattern of pure energy, condensed into form by the rules of confinement. You are not a collection of bricks. You are a beautifully sustained fire. Now, let's bring the observer into this picture. You, the one who is looking. In quantum mechanics, the act of observation is never passive. To measure something is to interact with it. To see something is to bounce a photon off it. This interaction inevitably changes the thing being observed. This is the heart of the famous measurement problem. A particle can exist in a cloud of possibilities, a superposition of many states at once. But the moment you measure it, it is forced to choose one state. With quarks, this principle is taken to its most extreme and absolute conclusion. You cannot observe a free quark because the energy required for the observation, the interaction needed to isolate it and see it, is the very energy that creates a new particle pair and keeps the quark hidden. The universe has a law against seeing its fundamental constituents alone, and the act of looking is what enforces the law. It is a perfect, self-referential trap, a cosmic catch. 22. Reality, at its most fundamental level, refuses to be disassembled. It insists on being perceived only in its stable, composite forms. It presents you with protons, neutrons, and mesons, but it hides the quarks and gluons that compose them. It shows you the finished poem, but it forbids you from ever seeing the individual letters of its alphabet. What does this do to our idea of knowledge, of discovery? Science has always been a process of reductionism, of taking things apart to see how they work. But here, at the very foundation of matter, reductionism fails. You cannot take the proton apart to understand it fully, because the whole is profoundly, fundamentally more than the sum of its parts. In fact, the whole is the sum of its parts plus the frantic, furious energy of their interaction. The relationships are not just part of the story. The relationships are the story. The paradox is amplified. The mystery deepens. We build a theory on ghosts we can never see. We prove their existence by the shadows they cast. And we learn that the very substance of our world is woven not from things, but from the forces that bind those things in an eternal, inescapable embrace. So we must ask the question, what does this mean for you? Right now, as you sit here, the trillions upon trillions of protons and neutrons that make up your body are not tiny, solid marbles. Each one is a raging tempest of confined energy. Each one is a universe of its own, governed by these strange and unbreakable laws. The solidity of your bones, the warmth of your blood, the electricity firing in your neurons, all of it is an emergent property of these confined storms. You're a symphony of prisons, a collection of beautifully stable, self-perpetuating paradoxes. You are built from ghosts. You are held together by an invisible, unbreakable glue. The stuff of you is 99% pure binding energy. You're not a static object. You are a resonant pattern, a standing wave in the quantum fields that permeate all of space and time. This forces a radical reevaluation of what it means to be real. What is a real thing? Is it something that can exist on its own, independent of everything else? If that is your definition, then quarks are not real. They are phantoms, mere aspects of a larger system. But what if real means something that has a demonstrable, measurable effect on the universe? If that is your definition, then quarks are among the most real things we know. The entire structure of every atomic nucleus, the properties of every element, the very existence of matter as we know it, is a direct consequence of the existence and interactions of quarks. Their effects are undeniable. They are the cause, even if they themselves cannot be isolated as an effect. This is the philosophical precipice to which modern physics has brought us. Reality is not found in the objects, but in the rules that govern them. The universe is not a collection of nouns, but a set of grammatical laws. The quarks are not the words themselves, but the conceptual roots from which all words are formed. Our language, our intuition, our minds evolved in a middle world. A world of medium-sized objects moving at medium speeds. A world of houses and bricks, of cars and gears. A world where things can be taken apart and put back together. This intuition is a survival tool, not a guide to fundamental truth. When we try to apply that common-sense logic to the subatomic realm, it shatters into a million pieces. It is like trying to use a hammer to measure the temperature of a star. The tool is wrong for the job. The question, is a quark real? Is a broken question. It is a question born of a classical mindset, trying to make sense of a quantum reality. It is like asking what is north of the North Pole, or what sound does the color blue make? The question itself contains a flawed premise. The universe does not care for our definitions of real, it simply is. And it operates on a logic that is far stranger, far deeper, and far more beautiful than our own. And what of consciousness? What of the mind that is contemplating this right now? Here we step onto the farthest, most speculative edge of thought. This is not established science, but a philosophical whisper that follows from these discoveries. If the universe, at its core, is a system of information, relationships, and resonant patterns rather than a collection of little bits, what does that suggest about the nature of the self? Your brain is a network of staggering complexity. Billions of neurons, trillions of synapses, all firing in an intricate, ever-changing dance. This is the classical picture. But beneath that, it is a quantum system, a churning sea of particles and fields, governed by the same rules of confinement and interaction we have been exploring. Could consciousness itself be an emergent phenomenon of this quantum reality? Not a thing, not a substance located in a specific part of the brain, but a pattern, a vast, self-sustaining, resonant wave propagating through the quantum architecture of your neural network. Could your sense of a single, unified self be a kind of macro-level quantum coherence? A stable resonance in the storm? A way for the universe, which is built on relationships, to form the ultimate relationship, a relationship with itself. Perhaps your consciousness is a stable, composite particle of thought, an idea that cannot be broken down into smaller, conscious parts, just as a proton cannot be broken down into free quarks. The I that you feel is the color-neutral state of the mind. This is pure speculation, a ghost of an idea, but is a powerful one. It suggests that the mystery of consciousness and the mystery of physical reality may not be two separate problems, but two facets of the same, deep, underlying truth. A truth based on connection, not separation. On patterns, not particles. We began this journey by looking at your hand. Let's return to it now. It still looks solid. It still feels real. But now you know what lies beneath. You know that its apparent substance is a magnificent illusion, a story told by the frantic energy of trapped ghosts and the unbreakable forces that hold them. So, we return to the central question one last time. Are quarks real? The question itself has dissolved. It is a relic of an older way of thinking. Physics did not give us a simple yes or no. It gave us a more profound, more challenging, and ultimately more liberating understanding. It told us that the universe is not written in prose. It is written in poetry. The quantum fields are the deep grammar of existence. The fundamental forces are the syntax, the rules of connection. The particles we observe, the protons, the electrons, the photons, are the words that make up the story of the cosmos. But some words, the most fundamental ones, cannot exist in isolation. A quark is like a root morpheme in a language. A unit of meaning like ject or spect, it has a powerful meaning, but it can only be expressed when bound within a full word like eject or inspect. It has no life of its own, yet it is the source of countless expressive possibilities. Quarks are the secret alphabet of God. They are the letters that can never be spoken alone, but from their combination, every star, every planet, every living being is written into existence. You are not a machine made of parts. You are a story. You are a sentence in this cosmic language, a sentence that is complex and self-aware and able to wonder about its own structure. This is the ultimate gift of this journey into the heart of matter. It is not a set of neat answers. It is a state of enlightened wonder, a state of awe. The search for the ultimate building block of reality did not lead us to a final, tiny speck of dust. It led us to an invisible, unbreakable relationship. It led us from substance to structure, from objects to rules, from matter to music. The mystery is not in some far-flung galaxy. It is here. It is in the weight of your own body. It is in the silent, violent dance that rages in the heart of every atom you are made of. You are made of paradox. You are woven from a force that both creates and confines. You are a testament to the fact that the most fundamental things in the universe may be those that can never stand alone. And in that realization, you might find a new kind of connection. A connection not just to the world around you, but to the very fabric of reality itself. A reality that is more mysterious, more interconnected, and infinitely more beautiful than you ever imagined. The search for knowledge does not always bring the comfort of certainty. Sometimes, its greatest reward is to replace our simple questions with far more magnificent ones, and to leave us, finally, in silent, reverent awe of the mystery that we are.